This talk is part of my seemingly endless crusade about simplicity. Simplicity in programs, simplicity in hardware, and hardware is not free. And I think the greatest magic trick of the last few decades has been chip vendors and hardware engineers making the hardware disappear. It was always there, but it just felt like it disappeared. So now the bad news is that the free lunch is kind of over. And some people realized this 10 years ago in certain systems, but for the most part, if you're looking at the cloud or doing something that's not super critical in terms of power and area, you may not feel it. There's still an abundance of hardware, but basically the effect is that frequency stopped scaling 10 years ago. Intel stopped pushing gigahertz. There was an ITRS roadmap in the late 90s that said that we were going to have like a 20 gigahertz processor by 2015. That didn't happen. Frequencies flattened out. Power, if they would have kept pushing power the way they were in the 90s and the 80s, we would have had a 2 kilowatt chip today. But of course, there's no way to cool that, so that's not going to happen. ILP, instruction level parallelism. The idea is that we can just have these super duper hyper-threading dynamic schedulers, and it'll just schedule everything automatically, like an auto-parallelizing hardware. That didn't happen either. And so what we see here is that everything kind of flattened out. Now, so what are we left with? How are we going to get more performance? Because 80s, 90s, 2000, you could set your watch by Intel's progress. Basically, double the performance every 18 to 36 months. And so if you had a program, wait for the new chip, recompile, or even run the same binaries, it'll run faster. So this is now over. Now who would care? I mean, actually, this is a very complicated question. I figured that when I started the company in 2008, I figured there's no such thing as too much performance. Everybody always needs more performance. But what I've found is that in 7 years it's become harder and harder to find those special applications that need that performance, because processors today on the desktop are incredibly powerful. I mean, if you have, let's say you have an Intel i7 quad core running at 2 or 3 gigahertz, that's the equivalent of running 10 or 15 billion instructions per clock cycle. You can probably do most programs, certainly email or web browsing or something like that will work just fine with that many clock cycles. And if it doesn't, something's really wrong. But there are applications that need it. They just don't exist yet. Search kind of far and wide. What are the things that we've located? And I've seen that people need more performance, but not just more performance at less energy. That's the interesting problem. And so one is communication. The idea is that communication is still exploding, right? It's still at an exponential pace. When everybody wants their individual stream, right? So it's not TV or radio anymore where everybody's broadcasting. Everybody wants a Netflix stream to their device, right? So now you have 9 billion people, everybody demanding a complete video stream. That's kind of the peak. Now, so that's one stream, but what as we get to the IoT phase, what if you now have 50 billion sensors that are streaming data? So that's, every communication company will tell you that it's still exploding. And yet the boxes can't get any bigger. If anything, the boxes should get smaller because you need many more boxes to have that kind of capacity. So if you have a certain size box, you can only get so many watts out of it. That's physics, right? That's thermal laws. So if you want to do more work in a certain size box, well, then you need to consume less energy per work. Same thing, robotics. There was actually just an article that came out this morning about how we're going to make robots smarter. Well, we can use the cloud. That's a really bad idea. I mean, and this actually came out of somebody at iRobot that said that yes, the solution is today the robots are stupid because we can't cram enough processing into the robots, right? It requires a whole cluster. And so what we're going to do is we're going to set up a radio, communicate to the data center, and then do the crunching and get a response. I don't really want the robot that has that kind of latency in terms of his response time. So it has to be local. So we want to put a cluster inside a tiny device, whether that's a robotic for assistance that's on 2 legs, on 4 wheels, or on the drones. So drones, let's say you want to, it could be anything. I mean, drones is pretty hot right now. It could be search and rescue, it could be farming, it could be news reporting, pretty much anything. And the idea is that you have these very lightweight drones, but of course physics says that you have to lift off, right? So you can only have so much payload. And let's say we put the payload at 100 grams. 100 grams is not a lot of processing. You certainly can't fit a modern heat sink and a 200-watt Intel processor on it. You need something that weighs nothing. And so that's another great one. The last one I'm a little bit ambivalent about. I think there should be a huge need for more processing in data centers. DARPA's talking about exascale computing. Google, Facebook, everybody's putting huge data centers. The truth is, nobody really cares about energy efficiency in those domains. They talk a lot about it, but if they really cared about it, they would change the whole architecture. Now, of course, the problem is that the software infrastructure today is so intense and so big that there's no way to do a clear-cut switch. I mean, for example, what's the difference between a 1 megawatt data center and 25 megawatt data center? That's the difference between running a city, right, or having a data center. And so, but again, 7 years of trying to come up with a more energy efficient computing solution, it all comes back to the software. And so whereas the first 3 ones, there is no choice, physics says you cannot build it, right? You cannot build a robot that's small enough, a sensor, a drone. The data center, you can always build a bigger data center if you have enough money. You can build a nuclear reactor to power it. It's a solution. It's a very poor solution, but it is a solution. You cannot cheat physics. So how many people here know hardware design, electrical engineering? Okay, cool. So this is like engineering 101 for high school, right? But let's not forget it. So the most important thing is power, and this is just one part of power, the top one. But the idea here is that how do you affect power? One, you can bring the voltage down, but that's kind of tough beyond a certain level, because that's you're getting down to things like thermal noise and thresholds and solid state physics, where you cannot really bring the voltage down too much, or your circuit will start failing. Of course, if you can bring it closer to that edge, you'll have circuits that fail sometimes and sometimes don't. But then you'll gain a lot. Of course, you need the programming model to be able to handle that. So you can play with the voltage, you can bring the frequency down, but that's actually not that interesting, because if you bring the frequency down, you also bring the performance down. So you got a no net gain. And the last one is capacitance, right? So if you look at the right-hand side, CMOS circuit, right, which is a staple of all of chips for the last 30 years, when you wiggle capacitors, you basically burn power. And so what you need to do is you need to reduce the amount of capacitance. So how do you do that? You reduce the size of the devices, so you scale down in process. But the most important thing is you use less devices, less transistors. So the less transistors you can use, the less power you use. And so the whole thing becomes using less silicon. That's the whole goal. And SRAM storage, right? So whenever you have a bit of storage, this is what you're using. Whenever you're doing a computation or control, you're wiggling some gates. And the key here is the price of hardware is not zero, right? It's getting smaller every year and has been, but that is also saturating, because Moore's law is ending, and we can't go down to 0 nanometers, right? There is going to be a physical limit. And so at the end of the day, every transistor has a cost. So this is a 5-minute introduction to Verilog. So I'm going to teach you everything you need to know about Verilog in 5 minutes. And this is pretty much all the syntax I used to design. I can design a 1,000-core chip with the syntax. I mean, it's trivial. Sorry. So first one is is module, right? This is the basic level of hierarchy, right? So what you do is you define a module with an interface. There is no magical leaps here. Everything that you want to interface to this module has to be an input and output. It's based in physics. So you have pins on this device. But now once we define this module, we can then instantiate once, twice, or 1,000 times across the chip. So this is how you do modularity and reuse. And this is, again, by having many layers of hierarchy combined with symmetry and architecture, you can actually design a very, very large chip very, very easily. And there's a lot of parallels here between software design. You have to declare your wires, right? So because a wire is connecting 2 points, right? So you should be declaring it. A register is a storage point, a piece of memory, 1 bit. And of course, in hardware and Boolean logic, every bit has to be specified. There are no fancy types, right? There are no integers, no floating point values. There are bits, right? And all the assignments are explicit. So there are no such thing as byproducts you say A is equal to B and C. And that one of the coolest things about writing Verilog code is that there is no order to your code. You can have 10 files with assigned statements, and they all happen at the same time, right? So you can have, when you look at your code, you can move code up or down on the page. There's no top of the page to the bottom of the page. It just happens, everything happens at the same time. And so how do you then order your design? Well, you use this, something like this always at, which always at event, do something. That's how you do it. So this is very much event-driven design. And the master event in most designs today is a clock. So you say, always at pause edge of clock, do something. And then, of course, you can, to make things simpler, you have case statements, if, else, and other things. And of course, a bunch of operators to do all the Boolean logic that you would imagine. But it's not as difficult as some people make it out to seem. Hardware design is pretty easy. In fact, I would encourage you, I'll show you something about the parallel board later. I would actually encourage all of you to, if you have a parallel board, if you don't, you'll buy one. But if you have one, it has an FPGA in it, right? Field Programmable Gate Array. So you can actually synthesize your own hardware, wiggle some LEDs, wiggle some pins, and see it work. It's, I think it's liberating, right? Liberating to see what how the other side lives. So this, I've been doing chip design since 96, so almost 20 years now, and especially this came in last 8 years. Things I've learned about the future of hardware from building hardware. And number one is obvious, massive parallelism. That comes from the first slide. I think it's indisputable fact. Nobody's going to argue that. The second one, Amdahl's law, is the law of diminishing returns. If you really want a 1,000,000 times speed up or 1,000 times speed up, there cannot be any serial component in your program, 0, right? And this applies to so many things, right? If you want a 1,000x improvement in energy efficiency, right? You need to improve all components of the system by 1,000x. So what that means is, the biggest lesson for the Amdahl's law is that this whole idea of having a threading model, right, where you have one master, right, that then pushes things out and then collects results coming back, like a fork join model, can never work. It will never scale beyond a certain number of threads. So you can't have this coprocessor domain either. You need something where you unlock that Amdahl's drag and Amdahl's bottleneck. The third one, thermal density. The smaller we make the chips, the hotter they're going to get per square millimeter. And that means that we're going to have a hard time running them at the peak performance. And that just comes down to we run it using CMOS logic, and we saw that first equation. Power depends on frequency and capacitance, right? So as we scale the devices down to 14 nanometer, 10 nanometer, capacitance goes down somewhat, but not as much as we would like. And so things get per millimeter hotter and hotter, and it gets harder and harder to extract the heat out of it. So we have something called the dark silicon phenomenon. And so what it means is that we're going to have to start turning on things selectively on the chip and in software, right? Or in an operating system or runtime so as not to make the chip burn up. Failure rate. This is very natural. As we move down to smaller and smaller geometries, we get closer and closer to quantum mechanics, and we have a harder time. We're not in the kind of the macro physics anymore. We have a harder time controlling whether things fail or don't fail. So things will start failing. At the moment, people know how to do robust systems at the macro scale, at the clusters, right, using Erlang. At the chip level, people still assume that every single bit will be perfect. And that needs to change drastically. And right now, we started seeing this at 28 nanometer, where there was some back and forth between silicon foundries and chip companies doing microprocessors, and they were kind of pointing the fingers, saying, no, your process is bad. No, your design was bad. That's the way it wasn't yielding. And the truth is that we cannot expect a silicon foundry to build perfect devices. So the idea is things will start failing. Get used to it inside the chip and at the system level. The number 5, the I/O bandwidth. Chips for the foreseeable futures are still going to be planar, and I/O is mostly going to come out of the sides. And so things are going to be I/O limited. You have to conserve how you move data. There will be 3D scaling. This is very clear. The economics of it have said that it's too costly to do it. But now that Moore's law is slowing down, there's more incentive and people are working on it. So this is a pretty easy one. And the systems that are going to be built are going to be amazing. Because if you look at today's systems, and you look at a motherboard, look at an iPhone or a MacBook, I mean, they are very, very dense. But still, the amount of silicon on that board is less than 10%. 90% is board space and connectors. So you can imagine making even denser systems by stacking. Energy efficiency. If you were to take just 1,000 Intel processors, x86, put them on a chip. Well, one, you couldn't do it today, but let's say that 5 years from now, maybe you could, but it would be a monster. It would be very energy efficient. So the guys working on the drones and the robots, they could not use that system, right? They need something that is much more efficient. So what we start seeing is heterogeneity, right? So we start seeing specialized processors for different functions. And so that's how we overcome the saturation of Moore's law, in that if process doesn't give us a free lunch anymore, then we have to be smarter about the way we do the work. And this is going to make programming them much more difficult, because now you don't have this homogeneous processor framework, maybe SMP, where you can just kind of write your code and it just works. Now you're going to have to program accelerators, big processors, small processors, keep track of things with special instructions, just so we can reach those performance targets. Productivity, right? So it's, at least to me, it seems unlikely that there will be one language that can rule them all. There will be a combination of domain-specific languages, communication languages, computation languages that needs to be mastered in a system. Number 9, right? So the programming has gotten easier and easier for decades now, and now it's going to get harder. I mean, at least to me, it seems pretty clear. Now, the good news is that compared to let's say the 80s, when programming was very hard, where you had to watch how many bits you were using in a program, maybe program in assembly, but everything was quite proprietary. It really wasn't an open source collaboration. Today, with all these concerns that are coming up in programming, things are going to get very, very difficult. But the good news is that we now have a much more robust open source collaboration model so that we can move forward faster together. So what is the architecture of the future? So there's 3 programmable architecture of the future. There's the 3 main contestants right now that if you see around the industry. One is the kind of the SMP model, right? So I've drawn here a blue box for memory, red box for a floating point unit or a computational unit, and green for memory. Just a kind of a cartoon illustration. So SMP, right? This is the traditional Intel world. For those of you who like Intel Xeon processors, this is it, right? You get 4 cores, 8 cores, 16 cores. Now Intel is working on an x86 with 64 cores, I think, or 80 cores. But the idea here is you have coherency, right? So you always know that your memory hierarchy is intact, and that's the SMP world, right? Then you have SIMD. SIMD is more like a GPU, where you have tons of computational units, and you only have one sequencer. So everybody works in lockstep. So you write a program like add up 2 vectors, right? So you add up vector A and vector B, and that vector can be 32 wide, 1,000 wide, but the programming model is everybody works in lockstep. And of course, and then the third one would be, well, let's have a completely distributed system where you have tons of processors connected by some kind of network, and each processor has its own memory, its own scheduler, and its own computational units. And there is probably going to be some combination of all, right? So the SIMD in a GPU is not really completely SIMD. There's some independent scheduling there of the threads. The SMP, of course, every SMP machine has some kind of SIMD inside, right? Maybe a Neon or AVX. And you can certainly combine some of the SIMD concept in distributed computing as well. But those are some of the kind of directions that people are jousting with right now. And there's a lot of buzz and hype, as you could expect from chip companies. So this is the architecture that I came up with in 2008. And the idea was just distributed architecture, and very, very simple. And this is, from a design's perspective, it was all about designing one small tile, self-contained, encapsulated, that contained all the functionality, including memory, compute, and networking. And then step and repeat that tile to infinity. So the idea was there's nothing shared in the system. Sound familiar? Nothing shared? The way you communicate is ideally by messages. So you would have one process running on this core, maybe another process running over here, and to communicate with 2 of them, you would pass messages. The architecture itself is actually a distributed shared memory architecture, and the reason for that was not to have to actually do loads and stores from other cores at abandon, but to open up for different programming models, right? So you say, what's the easiest way to pass a piece of data from here to here? Well, how about a memory transaction? And we can build messages on top of that in software. So we built a chip in 2011 with 64 cores. This was a prototype, and it worked beautifully. Reached 100 gigaflops, 2 watts of power consumption, and some pretty impressive specs. I mean, 50 gigaflops per watt is still by far the most efficient chip in the world today. And this is 2015, and that was 2011. And my only amazement is that it hasn't, I mean, we're doing well, right? But that it hasn't taken over the world yet. And I'll get to that part later. Why wasn't there more interest in something like this? But the chip itself, 64 cores in a mesh network with high-speed I/O to connect to a main processor or other chips. Coming back to physics, right? So when you look at the specs, the data sheets, and the performance, it's easy to get lost. But the true number that you should always be looking for is how many square millimeters of silicon is a chip using for a certain amount of performance. That's really hard to cheat if you normalize it on the same process node. And this is not meant to say that one core is better than the other, but the point is that when you look at a core, a CPU core, you can have anywhere from a monster like the Intel Haswell, a very powerful core, but that burns a lot of power, down to a tiny Epiphany core, which is, not as powerful as Haswell, but still pretty decent, runs at 1 gigahertz, but is 1/100th of the size. What can be done with that, right? And how far can we go? How simple can we get to? So just a couple of wake-up calls. Von Neumann specified a long time ago, one of the many things he did. That's Richard Feynman up there, who said there's plenty of room at the bottom. But Von Neumann specified that, what is the energy needed to move 1 electron, right? And so it's 10 to the minus 20 joules, tiny amount of energy. What do we use today to wiggle an inverter at 28 nanometer? Something like 10 to the minus 15 joules. So there's 5 orders of magnitude difference between what is the best in class, limited by physics energy, and what we do today with these kind of very robust, let's flip a 1 or a 0 complementary CMOS. So that's a big difference. So we know there's still 5 orders of magnitude difference. So 5 orders of magnitude, that's that could make my my iPhone last for longer than 12 hours, right? So it's a big deal. Take another one, right? Look at the biggest supercomputer in the world today, Tianhe-2 in China, 33 petaflops, 24 megawatts. That's a pitiful number, right? That's 1 gigaflop per watt for a system, right? So they have either a coal plant or something like that powering this computer, and you can do better, right? We can definitely do better. And when you look at that thing, this is now a machine that takes up a big room. How small could you get it? Could you make it? So if you look at the actual silicon, right, 12-inch wafers, how many wafers would you need to produce that kind of performance? And it's 16, 28 nanometer Frisbee wafers, right? So kind of like that Frisbee. That's the size of the silicon performance, the raw size. Now, of course, even at 50 gigaflops per watt, that would still consume a fair amount of power, right? So you couldn't possibly draw out hundreds of kilowatts out of a Frisbee, right? It's too thermally dense. So you'd have to make it bigger. But just in terms of silicon efficiency, there are so many orders of magnitude here. And I'm not talking about some kind of theoretical physical calculation. I'm talking about things we can build today to what actually people build. So it's an enormous advantage. This actually works, right? So we had customers and partners that have shown that looking at real work, real benchmarks, that this many core domain beats the traditional Intel processors by 25x on energy efficiency, right? Things like FFT, things like password cracking, and other compute-intensive things. And kind of cool, right? It can even be programmed by students. So a bunch of students at Australian National University took it on and ran benchmarks, stencil benchmarks, matrix multiplication, FFTs on the 64-core device, and they got to 85% of peak performance. And so this is not the experts at Ericsson. This is not me who knows the assembly. This is students off the street that did this. So I thought that was quite a nice one. But so we have some good things that happen, but we weren't winning over the massive software community, and really very few people knew how to do the parallel programming. So we started this thing in 2012 called the Parallel Board, and I always walk around with one in my pocket, but it's a credit card sized computer, kind of like the Raspberry Pi, and the idea was really to do for parallel computing what Raspberry Pi is trying to do for programming in general for everybody. Before we did this, we were selling our evaluation kit for thousands of dollars because that's what they cost to us. We couldn't give them away for free. We didn't have that much money. And we also slapped NDAs on them, right? So anybody who had to work with us had to sign an NDA. So that was like a perfect filter for keeping out everybody was interesting. And so in 2012, which was a scary step, but we did this because that's what everybody did. Every parallel processor company we'd seen that came before us, That's what they did. They sold their kits for $10,000 to $25,000. Everything under NDA, only worked with the biggest companies. And so, we just did what everybody else did. 2012, realized that was dumb, and we should do something new. So we bring the price down so everybody can afford it, open up our documents, our architecture reference manuals, open source all the drivers, all the libraries, and we launched this thing on Kickstarter. And it was pretty amazing. So we raised about $900,000 in 30 days, and it took us quite a while longer to ship them than we wanted to, but in the end, we shipped 10,000 units, 6,300 to Kickstarter, and then another 3,700 to pre-orders, all over the world, including 200 universities. So now these things are out there. So it's basically one per person. So you can now imagine roughly 10,000 developers who want to do parallel programming on this device. So just to put that in perspective, right? You look back 20 years, right? 1993, in Boston, the CM5, at the time, the world's most powerful computer. It cost about $30 million, and 136 gigaflops at 100 kilowatts, right? So this was a beautiful but massive computer. Today, 2014, the 64-core computer, $199, and about the same performance. So in 20 years, our computational performance has stayed the same in these two cases, but the cost has gone down by many, many orders of magnitude, which makes this kind of performance accessible to everybody. But 64 cores is cute, right? It doesn't, like Joe said, he wants 1,000 cores. So we have a big roadmap. So this data points are anchored on our devices today. So I talked about silicon efficiency, right? So if you know how much silicon you use at 28 nanometer, and you know what the maximum size that you can do, then you can figure out what's the biggest device we can make. There's no doubt in my mind that today it's possible to build a 1,000-core device. Anybody could build that today. And in 2018, we're going to be able to build a 16,000-core device. So I consider that a fact. Will Adaptivo be able to build it? I don't know. It depends on a lot of economics, right? If we do well, maybe we go out of business, maybe we don't survive. But I think it's an imperative that somebody needs to build this. If it's not us, I hope it's Intel or somebody else. So when we had that many cores, what does that mean for the programming model? What does it mean for all of the software infrastructure? So this is something that I am now working on. I was hoping to have more details about it when I came to present, but this is pretty much all I can give today. But we are working on something. So it's 1,000 cores on a chip, and this is for this year. 1 gigahertz operation, 32 terabytes per second of local memory bandwidth, 1 tera messages per second on chip. That's a lot of messages. All of this in about 10 watts. So what do these specs mean? Well, it's this is not a GPU, right? Let's be very clear, because the GPUs today have specs that maybe get close to this, but this is again 1,024 independent RISC processors. They can all run a complete task. You can have 1,000 independent and separate tasks here, right? So I think if nothing else, it shows what can be done. So what does programming such a monster look like? Well, there'll be some new things. One, when we build this 1,000-core chip, not all cores will be working. There will be some cores that will not be working on the manufacturing because we can't reach the yield. So you'll have these blackout spots here. And so when you think about the runtime environment of the programming, if you assume that all cores are working, you're going to be stuck, right? Because we won't be able to produce it. Second one, there will be intermittent bit failures. With this much SRAM on chip, it's likely that there will be soft errors. once in a while. So what do you do about that? So the scheduler needs to be smart enough to never schedule something to a core that's never going to work, and smart enough to be able to kill a process that got hung, right? Or the fact that that process that got stuck doesn't ruin everything else on the chip. So this is just a fault tolerance robustness, right? So this is the first thing. Second thing, clearly when you have that many cores on a chip, traffic congestion becomes a big deal. So in the chip world, in the 1980s and 90s, we used to do everything by hand, right? We did schematics, we drew little polygons to draw gates and transistors and wires, and then that was just so inefficient that at some point somebody extrapolated that to build the next Pentium processor after the next one, sometime in the 90s, you would require every person on Earth to do it based on X number of transistors and number of transistors per person per day, right? It would require all the people on Earth to build a chip, which obviously didn't happen because the tools and the methodologies became better. So the productivity of a person went way up. I mean, just for example, I think in the 90s, the rule was 25 transistors per day, per engineer. That was the efficiency, right? Kind of like a lines of code. This 1,000-core chip, we're going to do with 3 people, and it's going to have about 4 billion transistors. So if you look at, let's say, 6 months, 3 people, 4 billion, that's way more than 25 transistors per day. And this is, we've already done this. We did our 28 nanometer chip in 12 weeks with 3 engineers, and that was 200 million transistors. So the productivity is okay. Now the one thing to note here on the congestion, right? So like I said, we started out with schematics and transistors back in the 90s, but then the complexity got so big that we had to use machines, tools, to do it for us, right? So people invented EDA tools, things that did automatic translation from RTL to gate. So the Verilog code that I showed, there's now tools, incredible tools with millions of lines of code that translate that to super optimized logical gates, CMOS gates. And again, the parallel with software, right? So in the beginning, you would have a camp that said there's no way to build an EDA tool that can do a better job than people manually optimizing Boolean logic, right? That's kind of a weird statement, but it was absolutely a belief. But the only problem was it was just that the EDA tools hadn't caught up yet, right? Today, nobody would ever write logic with gates. You always synthesize. You write in a high-level language, and you have a compiler that compiles it. Same thing with layout. 10, 15 years ago, a lot of high-end processor companies would do manual layout to compact the gates together to make the silicon size as small as possible. Today, the EDA tools that do place and route are amazing, and the complexity is such that there's no way to manually do it. You need automation. And so at 16 cores, 64 cores, you can maybe do the manual threading, manual communication, and manual placement of tasks. At 1,000 cores, you need machine help. So at this scale, there's definitely need for a place and route methodology for placing tasks, a very, very smart scheduler to minimize congestions and latency and energy and so forth. So today's chip design tools all have these things built in, right? So when you run a chip design process, you have knobs that optimize for power, for timing, for area, for integrity, and so forth. And you're generally doing this statistically over a certain range, right? So you might even be running Monte Carlo analysis to figure out what's statistically the best way to produce this thing. And we are going to get the same kind of uncertainties here, which we've never seen before, because again, until today, every chip was perfect, and it's no longer the case. Energy. These energies are a little bit, let's take them with a grain of salt, but they're more or less correct. It depends on which process node you're in. But basically, what it means is that there is, computation is one thing, moving data on chip is another thing. Moving data off chip is a whole other thing. And so you need to minimize all of them if you want to minimize energy. And the idea is, don't move data unless you have to. Keep it, I mean, it's pretty clear, don't compute if you don't have to, but also don't move data unless you have to. And so if you want to minimize energy, you really want to communicate only with your nearest neighbor, not to the edge of the chip, and never off chip. And this is not, not something probably most people think about. Today, if you look at a CPU-based system, you have a cache hierarchy in there, and the cache controller is continuously shuffling data around without anybody really paying attention, unless sometimes you get cache thrashing and then people realize there's a problem. But it's pushing data off chip all the time and burning all kinds of energy outside of your control. Same thing with the GPU. GPU has such an incredible amount of DRAM bandwidth to bring data in that you can probably put all your data in, a lot of your data in DRAM and still get good performance. Of course, you're wasting huge amounts of energy by moving data all over the place, but because there's such a high level of bandwidth, you can get away with it. At something like this, if you really want to minimize energy, you need to think about locality. It's locality, locality, locality. So future programming is going to be pretty rough, in my view. It's going to be really, really hard. If programming was hard today, it cannot not get easier, right? Because now we're bringing new concerns in that are going to make it harder. But I do generally believe that it's just a matter of the tools catching up. And if again, drawing a parallel from hardware design, every node that we did, right? We started at a 0.18 micron, 0.13, 90 nanometers, 65 nanometers. Every node we got a huge new concern that we had to deal with. And so at like 0.13 micron, it was like voltage rail drops. At 90 nanometer, it was signal integrity. At 28 nanometer, it was variability. At 14 nanometer, it's yield. And so we have, EDA companies out here in California, Synopsys and Cadence and Mentor. They get it done, right? So they, huge engineering teams that build the tools that let the designers not worry about these things. And so to me, there is an enormous need here for the tool makers, right? The people working on the programming languages and the SDKs and the tools themselves to figure out how to make the programmer not worry about the majority of these things. So the programmer can focus on the really important stuff. So, I mean, because this list is pretty enormous, right? So if you look at most programmers, right, one, get it right, get it correct. That's not easy. That's not that easy. And then once you have it correct, then you start mucking with the code and making it faster, and then you start breaking it, and you spend a lot of time optimizing it. And that's a whole thing. Now, if you have to add 5 or 6 other optimization constraints, psychologically, I know programmers who won't be able to deal with that, right? They're going to get stuck in an infinite loop of optimization, and for things that it's too complex a problem that it really needs automatic tools. I have one more slide. This is my plea for help. So again, I've been doing this for 7 years, and I can. And before I did it, there were tens of parallel processor companies that tried this as well. Companies like the Transputer, right, or architectures like the Transputer 20, 30 years ago, Tylera in Boston recently, and many, many others. And the success rate is 0. 0 out of n have succeeded. And I would say that in the past there was a very good reason for it, right? Moore's law was still marching along. Intel and others were producing general purpose processors every 18 months, got better and better. There was no purpose for them. Now that things are slowing down, there is a purpose. But the software ecosystem is so entrenched in the old way of doing things that the kind of the energy needed to escape this this kind of von Neumann energy well feels like infinity, right? Certainly infinity for a startup company. We can't do it. So So it's all about the software. And so we built the hardware, we built the boards, it's out there. The last few months, we started focusing on, right, it has to be the software. We're not going to build hardware until the software catches up to it. So the 1,000-core chip, as sexy as it may be, it doesn't matter, because today we don't see that people know what to do with 16 cores or 64 cores. And so the 1,000 core is just going to sit there on the desk, and it's not going to do anything. So we have a few things going on. One is this open source standard library built for parallelism. So when you think of standard libraries in C, they were formulated in the 80s, and they don't have any parallelism built in, right? You compute on a scalar. And then, as things evolved, you start getting POSIX calls for mutexes and threads and things like that. But nothing is built for many core the way you would do it if you built it today. So we started this effort. We're going to keep working on our own, but we clearly need contribution. There's about 200 functions in there right now. Pick a function, contribute. We'll honor the pull request. So please. VMs, I really hope there can be an Erlang virtual machine running on the Epiphany cores. The future cores will have 64 kilobytes, which is a massive improvement of the current 32 kilobytes. So I don't know what the VM is today, a couple of megabytes. So all you have to do is reduce the size of the VM by a factor of 100 or so. No problem. But it would be incredible, right? So I hope there's some way to either, tweak the model, the usage model, or to get something that's close. One thing that we do have, so we don't have hardware caching built in, because to be honest, I didn't talk about that, but when you start having 1,000 cores, let's say you have a traditional 1,000 cores with a cache hierarchy, a kind of a multi-way cache miss, cache hit kind of thing. What happens when you do have a cache miss? And you're going to have that probably 1% of the time. And you have 1,000 cores. So you have 1,000 cores with a 1% cache miss ratio. So they're all going somewhere. Well, where's the DRAM? Where's the second level store here? Well, somewhere off chip. And if 1% of 1,000 cores starts thrashing that DRAM asynchronously, your performance will go to nothing. And so there really isn't a way to make a hardware caching algorithm smart enough with asynchronous process to make it work. And so the only way to do it is to have software caching, where it's under the control of the application. And so this is what we've done. So we didn't put in hardware caching, we put in software caching. That may help some programs that are larger than 64 kilobytes, which there definitely are some. And the next thing is we've had a very, very hard time finding people who speak our language, meaning people who know parallel programming. When I go into and talk to friends at Ericsson or at government labs, supercomputing facilities, absolutely no problem, right? Speak the same language. If I go more mainstream, they feel very uncomfortable. Usually the question is, how are we going to program this thing? And usually within a couple of minutes, based on the questions, I realize that this is not going to work out. Right? We can't afford to take them through the learning process of becoming parallel programmers. And so I think that's where we need a huge amount of help as a kind of, if we think over this as a parallel programming community, in showing the way. I would say 99% of the programmers don't know how to do parallel programming. The last one, this is, I don't know what the answer here is, but certainly it would be fantastic if we could start teaching parallel programming at the base level before people pick up the bad techniques, right? So, for example, right, I've been programming Verilog for 15 years, and then when we got the chip out, I decided I'm going to do a parallel matrix multiplication algorithm on our chip, and started writing in C. And I don't program a lot in C, but so the Verilog code where any statement on the page happens at the same time. There's no order to it. And then I programmed this thing in C, and I was passing data around. And I couldn't figure out what was working. And within 5 minutes of going from Verilog to C, I was reading the code like this, right? But all the code over here on this processor was running in parallel to the code over here, so there was no significance to the order of it. And so the idea is that, things happen asynchronously is a tough concept to teach, and it's probably better to teach it at the beginning. So, can we at the high school level get in and teach people the right way instead of reteaching them after 10 years of bad habits, or even 5 years of bad habits if you go through college. So that's my plea for help, and buy a board, okay?
Wonderful. Round of applause.